we are going to explore different optimizers. We'll spend another 15-20 minutes on this. Okay, then I'll be moving on to the notebook and I will be showing three aspects. I have changed the notebook. I say change the notebook. I have introduced in this notebook. What are all the things is the trained model, how to save the trained, how to save the trained model. See, sometimes certain applications you develop, your training will go for several hours. You know, ChatGPT 3, it has run for a week, 1 week during the training when they have trained 700 billion model parameters involved in that. So it is a one-time process. So when you train it in the production, the trained parameters need to be loaded directly. So every time whenever I open the notebook, Python notebook, I don't want to retrain it. I don't want to waste the time. So once you are satisfactory with the performance, if you wanted to save the model, I'm going to show two variations. Okay, one is the manual saving method. Another one is the automatic save. This aspect I have introduced in the same notebook. We are going to see this. Number 2, this auto saving is based on using the checkpoint, model checkpoint. I'm going to use the feature called model checkpoint. I will show you how to make use of this. So both the mode I'll teach you, manual as well as, so the trained model, how to load, and you can use it for the prediction. That also we're going to see. The second aspect, how to give a user-defined metric. User-defined metric. Because by default, the metric is accuracy. Suppose during the training, in case if you wanted to monitor F1 score or a recall or a precision, how to define the user-defined metric and how you can call it. This is the second aspect. And the third aspect, yeah, we are going to explore optimizers. So changing different optimizers, and we are going to see the performance changes. So these three things I have introduced in the same lab 4 notebook. We are going to explore this. Okay, before that, I wanted to give some theoretical input regarding this optimizers, then we'll move on to the notebook. So theoretical means it's a mathematical perspective of those optimizers, what it really means. How SGD works? SGD works on calculating the gradient. Okay, so let me name the gradient Okay, let us name this gradient as dw. Okay, dw. The gradient calculated by your SGD function is called as a dw. So according to your, whether you do record by record training means individual dw, or it is a batch training means summation of dw. This is just a notation. But the actual formula, you know how the gradient is calculated, like dou E by dou W formula. Okay, this dou E by dou W formula, I just call it as a derivative. This is the gradient term. Now we are going to give a different representation, something like VDW is equivalent to beta times of VDW plus 1 minus beta times of this DW. So we are going to understand how we are extending the SGD to AdaGrad, adaptive gradient. So this is the first variation introduced after stochastic gradient descent. Okay. Instead of directly using this value and to update the weight, or how do we update the weight? once we calculated this, once after calculating this, how do we update the weight? So the W new equivalent to W old of the previous iteration, learning rate times, okay, learning rate times dW. This is how we apply the formula, right? Gradient term. Now, AdaGrad is going to use W new equivalent to W old minus eta times. Instead of dW, it is going to substitute VDW. That VDW is what defined here. Okay, this is mathematically okay, but logically what it means, we'll try to focus on. So what is the benefit? What is the benefit of using this? For the linear problem, I told this loss cost function will have a smooth convergence for a linear problems. But for a non-linear problem, this convergence won't be smooth. So there is a risk of local minimum. So your algorithm may get stuck in a local minima situation. Say it starts with some higher value, keep reducing it. Suppose there is some saturation point, again it's going down, and this is where the global minimum. Okay, this point is the global minimum. But once the algorithm reaches this point, okay, there is no further change. Your gradient is almost zero, right? What is gradient? Gradient means slope, right? There is no slope. You have reached the flat portion, is almost saturated. Your gradient is almost zero. What your algorithm will think that, okay, there is no further changes in the gradient, so there is no need to further adjust the weight. Your algorithm will stop, premature stop. You may think that, okay, my algorithm is saturated, but your global minima is somewhere here. Still your error will be high. So your SGD will not get rid of this. Okay. A classical SGD cannot get rid of this. If you use AdaGrad, AdaGrad can escape this. Okay, now let us see how the AdaGrad can escape this. So what we are going to do here, simultaneously we are going to calculate two things. Along with your regular gradient, we are going to calculate an additional term called VDW. Okay, we are going to calculate this additional term called VDW. Of course, this beta is it's our choice. Say for example, I have selected this 0.9. Okay, 0.9 for example. First, it will compute dW. So from here, it's calculated the gradient. Yes, gradient changes, gradient changes. The moment it approaches this point, what happens to my dW? My dW is going to be very small, isn't it? Say for example, I see simultaneously what you are supposed to calculate at every stage of dW. Say for example, in iteration 1. In iteration 1, let me write my dW as well as VDW. In iteration 1, I have got 34.6. Okay, 34.6. Initially, I don't have my previous VDW. So initially, I'll start with 0. When I start with 0, what is at the end of the first iteration VDW? I don't have previous VDW. So previous VDW, I assume 0. So 0 times everything 0. 1 minus 0.9 is 0.1. 0.1 means 10% of DW. Okay, what is 10% of DW is approximately 3.4. Okay, so I round off to 3.5. So at the end of the first iteration, my VDW is recorded like this. Iteration 2, your gradient got reduced somewhere to 26, assume 26. Now, how do you update your VDW? Your VDW is, now your previous VDW you got 3.5. So 3.5 times of 0.9 plus 0.1 times of DW, 26. So this is approximately, let us say approximately 3.3 plus 2.6. So 5.9. Okay, I am giving approximate score 5.9. Then iteration 3. Further gradient reduced to somewhere around 14. At this stage, what is the updated VDW? Previous is 5.9. Let me take approximately 6 times of 0.9 plus 0.1 time of 14. This is 5.4. 5.4 plus another 1.4. 6.8. 6.8. So likewise, at one stage, okay, one stage, your DW, when it reaches this place, it's almost a very small value, like 0.04. Or I give like a 0.4, assume. So it reaches a point called 0.4. So 0.4 is a very, very small gradient. It indicates that it's almost we are trying to reach a saturation zone. But we are not going to update the weight based on directly on the DW. Rather, we are updating the weight based on the VDW. Okay. So can you notice my VDW gradually increases? So what is your, forget about the mathematics. Okay. You forget about how I obtain VDW. You forget about it for time being. What is your perception on the VDW? How do you interpret the VDW? Imagine you are, after trekking, you have reached the top peak. Okay, you go for a trekking and you reach some top. From there, again, you are sliding down. You are running down. Okay. When you are running down, you are coming down, you are gaining momentum. Can you imagine this is something like you are gaining a momentum, you are speeding up? If you, even though if you try to walk, but it looks like you are running, because of the slope, it looks like you are running. You are making a very fast movement. Okay, the moment you reach this spot, then only you slow down, right? Your momentum will slow down. So it literally, your VDW is capturing the momentum factor, isn't it? It's capturing the momentum. That is why this beta spot is a momentum coefficient. Momentum coefficient. So what is the logical concept here is, even though you have reached this flat portion, your momentum will not allow you to settle down here. Your VDW will say that, okay, now you have reached the spot, your DW is somewhere 0.4, very small value. Okay, but your VDW will say that, hey, so far you are running very fast with a very high momentum. How come a sudden plateau will reach? Okay, so even though you have a DW is 0.4, my VDW will not allow my model to saturate. Because when you have DW reach 0.4, what happened to your VDW? Your VDW, let me erase this portion. Let us assume to reach this, I have got maybe 10th iteration. Okay, this is around 10th iteration. As you see, gradually this number increases. Okay, towards the 10th iteration, maybe my VDW also reach proportionately, say around 12.6, assume. Okay, it has reached like this. So my previous iteration, which is 12.6. Now I'm supposed to calculate in the current value, when the current DW is 0.4, what is the VDW? So for the previous VDW is 12.6. At the end of the 9th iteration, my VDW score is 12.6. Now apply the formula 0.9 times 12.6 plus 0.1 time 0.4. So this is approximately 12. Okay, 12 plus, can you see only 10% of my current gradient it is considering? 10% of the current gradient, 90% of your previous moment. 90% of your previous moment, and previous moment means 90% of your momentum, and only 10% of my current gradient. When it's going to take like this, you are going to have something called 12 point some value, and here you are going to substitute your weight update formula. Even though your DW has reached a very small value like 0.4, but you are going to substitute a higher number called 12 point something. Thereby, even though when your DW reaches a very smaller value, you are considering only 10% of it. The remaining 90% comes from your momentum. So thereby, it will not allow your model to get saturated in this place, because your momentum will push your gradient to this spot and it will keep moving it. But here, this is a comparatively larger plot. Okay, it will try to push. Even though it try to push, you will come here. Again, try to push, it will come here. At one point of time, your model will recognize, okay, there is no further movement, because your previous momentum also is slow down, right? Your momentum factor also is slow down. At one point of time, it will realize, okay, VDW also saturated. So VDW will come down. At one point of time, there won't be any changes in the W. So this is the logic behind AdaGrad. Is that clear? So the mathematics and the logical perspective can able to figure it out. If you have any questions, ask me on this. See, AdaGrad focuses on local minima trap, whereas RMSProp focuses on, there's another optimizer called RMSProp, which focuses on overshoot problem. Overshoot means oscillation problem. What is overshoot? Sometimes what happens because of wrong selection of the learning rate, or sometimes because of some very bad initialization of the weights or something, your gradient will, first two step, your gradient will gradually go down, and maybe the third step it will come here, again it will go here. It something like increases and decreases, This kind of oscillation affects these larger movements. So how to control these oscillations effect? If you're training, while training process, if you see your values are keep oscillating, you could try RMSProp. RMSProp will effectively control the oscillations and speed up the convergence. So how RMSProp mathematics is defined? The mathematics of RMSProp is defined using S notation. Whereas for AdaGrad, we use VDW, right? Here we represent SDW notation. Mostly these kind of questions are asked in the interview. Sometimes when you migrate to ANN based job profile, AI based job profile and all, irrespective of your experience, definitely some senior fellow will be there just to quickly cross check your knowledge level in the field of general AI or even computer vision or language model specific and all. These are some of the standard questions. They will easily touch upon it. So you should be able to tell logical meaning of it. They don't expect the mathematics. Don't worry about the mathematics. What is the formula? Nobody bothers about the mathematics. Logical idea. AdaGrad is basically using the momentum concept. It tried to escape the local minima while during the gradient descent. So try to explain in your own words. No need to give a Wikipedia answer. No need to give a standard book definition. What from your understanding, try to give you a genuine expression. That is what they expected. Otherwise, they can easily understand that, okay, you blindly memorize and you're telling somewhere from the Wikipedia definition, or just simply are throwing the jargon. They can easily figure it out. Whether with understanding you are telling, or with the superficial jargon term alone you are telling, they can easily figure it out. Look at the expression of RMSProp. RMSProp is using STW to adjust the weight. So W new is equal to W old eta times, it is substituting STW. Can you see how STW is calculated? It's calculated by squaring the gradients. See, not only this, while substituting, after substituting this value as TW, this is not the direct substitution. Whereas for AdaGrad, it's the direct substitution of VDW, but for RMSProp, your DW also you include in the formula. Okay, you are including DW also including in the formula, divided by root of SDW. So this is the formula. So like the same manner, we have to start with 0 because initially we don't have this code. So we start with 0. Again, we'll choose beta 0.9. So whatever the gradient you compute the squared of the gradient. Okay, squared of that gradient. It is something like an exploding gradient, right? Whenever your gradient is shooting up and the square of the gradient also goes up. Okay, this value, the overall, this STW value will go up, isn't it? Goes very big. So when this value goes up, very large value, it has to control that oscillation. This is called the oscillation, the higher value. It has to control it. So when this value reaches very high, okay, when the gradient grows very what we call this an exploding gradient problem. Whenever this exploding, the earlier one was a vanishing gradient. Why we call it a vanishing gradient? Because it looks like a flat portion. Your gradient is almost approaching to 0. What was the logic to escape this flat region is to give the same momentum push to this so that this guy will escape the zone and continue with this momentum. Here your gradient vanishes, okay. But other option is your gradient can explode. Okay, instead of reaching a plateau here, it may explode going here. Maybe that explosion can happen even after very good convergence. After reaching the spot, suddenly there is a very big overshoot can happen. So whenever a very big overshoot happens, what is the logic here is, but when you substitute the weight value, what happens? When the denominator, you substitute the large value. What happened? 1 divided by the large value. Actually, the original gradient is very big, right? The original value is very big. You are trying to scale the very high value with 1 divided by the large number. It's a very small. So 1 divided by, say for example, 1 divided by say 100, what happens? You have this value as 0.01, right? What actually happened? Your DW score, you try to scale with 0.01. Suppose your see this 100 I given SDW score is 100, okay, but your DW score is somewhere. It is a combination of these two terms. Let us assume you have got around somewhere like, but see, 100 is like a big number. Let me give 1/10. 1/10. So that means you are going to multiply with somewhere around 0.1 of something like this. Or say it is like, okay, it's like a 74.86. Let us assume the 74.86 is a very big gradient score, very big. At this point, your gradient has reached somewhere around 14. From 14, suddenly, because of overshoot, it reaches very high gradient in the opposite direction, 74.86. Okay. So what this guy will do, so you substitute this 14 square and all those things. We are not sure about what was the previous value and all. But what is the logic you should understand? If the DW is higher, okay, obviously the square also higher, but in the squared value, you take only 10% of it. Please understand. The squared number, 74 square something, you take only 10% of it, plus 90% of the previous SDW. So the previous SDW is highly impacted by the value closer to 14 or 12 or 10 something else. So, but however, still it is like a reasonably big number. That big number you divide by that big number, you get somewhere around 0.1, the scale factor. So 0.1 times of 74.86 when you do, you'll get a score somewhere 7.486. That means what? Whenever your gradient shift to 74.86, but actually what you are substituting, you are not substituting 74.86. You are substituting only 7.46. That is much closer to this. Okay, after 14, reaching 7.4 is reasonably good value rather than overshooting to the higher value. So whenever your gradient overshoot to the higher value, okay, this value will grow up. When this value go higher, when you put that in the denominator, it is going to scale down this value. So obviously, if does not shoot up, if your okay, if the denominator value is reasonably small, it is going to less affect this. Okay, if the denominator value is growing very high, it is going to affect this more. Otherwise, it is going to less affect it. That means it is understanding that you are converging in a good way. If it is less affecting means, whenever it's overshooting, I am going to control you. That is what this guy is going to do. Okay, whenever you are growing up, I am going to control you. If you grow up, naturally this guy is monitoring you. This fellow is monitoring you. Are you growing up or not? Whenever you grow up, this guy will inform me with a high number. So what I will do, I will scale down you. Simple logic. I will scale down. Whenever you grow up, I will scale down you. That is what this equation is telling you. So your RMSProp try to control the oscillation. Okay, in the interview perspective, how you can say RMSProp controls, okay, controls vanishing gradient or exploding gradient. Multiple choice question. RMSProp controlling the vanishing gradient or exploding gradient. Okay, whereas AdaGrad controls vanishing gradient. Why vanishing gradient? Because of the local minimum. Okay, because of the local minimum, vanishing gradient. I need to control, practically I need to control both, right? In a practical problem, I may encounter both kind of problem. That is why we have got Adam. We have got Adam. Adam is, it looks like a name of a person, but it's not. Generally, people think that, okay, maybe the person who developed this optimizer, they named after that person, they may think like this. Actually, it's not. Adam stands for adaptive moment. Adam intelligently uses the combination of, okay, if you use Adam, you will be more safer. Okay, but precisely you can observe the iterations and you can selectively, you can either use Adam or AdaGrad or RMSProp. It's your choice. But if you use Adam, you'll be more safe. Even the exploding gradient it will control, or also vanishing gradient also it controls. So your Adam expression is combination of both. I just give you the expression. So Adam uses both expression, VDW as well as STW equation. Since both equations going to use to differentiate the beta, okay, they have introduced beta 1 for this and beta 2 for STW. So beta 1 time of previous VDW plus 1 minus beta 1 time of DW. Here beta 2 time of previous SDW plus 1 minus beta 2 time of DW squared. That's why the squared term is coming. That's why it's called as a root mean squared RMS root mean square prop. So once these two terms are computed as usual, okay, the moment you have got DW, you'll be supposed to calculate this as well as this, isn't it? Once you calculated this, what you'll be doing is calculating additional term, something called VDW corrected. Similarly, SDW corrected for Adam. Okay, this is what we are learning. This is the equation for adaptive moment, Adam optimizer. So in Adam optimizer, what they are doing, once after calculating this, your VDW scaled by 1 minus beta 1. Similarly, your STW is scaled by 1 minus beta 2. And finally, this corrected term is used in the weight adjustment expression. So in the final formula, the weight adjustment formula, W new equivalent to W old eta times. It uses both the term VDW in the numerator corrected divided by root of STW corrected. Sometimes to avoid STW 0, chances are there, if 0 happens, to avoid a number divided by 0 to avoid infinity, it added a small constant. Okay, this small constant value is referred as 1e minus 8, that is 10 power minus 8, 0.000, very small number. So as per the original paper proposed, the Adam they proposed, okay, I'm just giving you the parameters. You don't need to adjust it. Okay, go with the default. This default itself worked very well. No need to modify anything. Beta 1 is 0.9, beta 2 0.999, and epsilon score is 1e minus 8. This is very optimized, very well optimized model parameters for Adam. Beta 1, beta 2, epsilon hyperparameters per Adam. So most of the cases you can go with the default value, it will work very well. No need to manipulate anything. Just you call the optimizers Adam, that's all. So Adam uses your momentum term as well as, what is this term? This term we use it in the RMSProp to control the exploding gradient. So the ratio of it when it's uses, it handles both. So it will control the weight in more controlled manner, irrespective of oscillations or irrespective of the local minima. Okay, this weight adjustment will go on very smoothly. So whatever this mathematics, whatever we have discussed in the past half an hour to the context of the interview point of view, but otherwise in the coding part, you can simply call the optimizer name. Okay, it's very simple and straightforward. Okay, now we'll return to this notebook and we are going to explore the other aspects, particularly saving the model. Okay, I'll show you how to manually save the model and reload the saved model, and also how to automate the process, loading and saving process. So what's the first step we do? Thresholding. After thresholding, we reshape to one-dimensional 784, because 28 by 28 we convert to 784 one-dimensional. After converting one-dimensional, I'm checking the shape. 60,000 training record, your 2D image converted to 1D row, and training records you have, validation record you have 10,000 records. And then I do the scaling. 255 and 0 we are converting to 0 and 1. That's what divide by 255 will do. Okay, yesterday we have compared the logistic regressor score. The overall score we have got 92. Okay, let us leave logistic. We'll straight away go on to neural model. Here we do the one-hot encoding, right? Yesterday we have discussed this. So 10 nodes in the output. Okay. So first I will show you when you compile and run. Can you see optimizer? I am trying Adam today. Yesterday we have used SGD. Today we are exploring Adam. And accuracy metrics is the default I told you. If at all, if you wanted to use any other scores like F1 score or precision or recall, you cannot use it directly unless otherwise you need to explicitly define this. We are going to define this. So actually it uses the actual formula. Whenever you present your actual label with the predicted label, how do we present the confusion matrix score, right? From the confusion matrix score, it is calculating true positives and predicted positives and possible positives. It applies the formula from your confusion matrix table formula. Just a few minutes before I have shown the calculation for sensitivity. Your recall is nothing but sensitivity. True positive divided by positive possibles. Okay. So if my COVID case is a positive I gave like 50, this is negative and positive. So this entry is called true positive, right? True positive. This is true negative. This is false positive. This is false negative. So true positive divided by positive possible positives. And for precision, what we do for precision, true positive divided by predicted positives. Predicted positives. Not only these 45 are positives, out of these 30 healthy people, 2% are declared COVID positive. That too also I should consider. That is what? True positive divided by predicted positive. The meaning of predicted positive is this 45 plus 2, 47. Out of the predicted positive, how many true positives are there? Only 45. So, and I'm taking the harmonic mean of both F1 score. So using the same function, if you are returning F1 val, you can monitor F1 score. Or if you wanted to monitor only recall, you can return recall. Or if you wanted to monitor precision, you can return precision. Just you rename the function. Suppose I wanted to return recall score, right? I just rename the function name. This is user defined name. You can use any name of your choice. So I name this as a get recall. Here I name it as a get F1. Or even you can name it like a my recall or my F1 score or my precision score. Any name of your choice, you can use it. And once you define it, okay, once you define it, say for example, I return F1 score. Okay, once I define this F1 score, now as usual, you construct the architecture. Once you constructed the architecture, I have to do the compilation, right? So in the compilation, look at the difference. Whenever you use the default accuracy your model understand should be entered in quotes. But once you have defined your user defined function, okay, so what function you are going to use? Get F1, right? You have to enter get underscore F1 without parenthesis. Okay, without any quotes. Now you compile your model and Now, if you run, yesterday when we run this at every iterations, what we have monitored, training accuracy and validation accuracy, training loss as well as validation loss. What kind of loss this is? Categorical cross entropy. Just at the beginning of today's session, we have seen categorical cross entropy, how it is being calculated from the predicted probability score, right? So now instead of accuracy we monitor, this time we'll be monitoring the F1 score. But understand, whatever the loss produced by the model remains same. Your loss, I cannot control the loss just by I change the monitoring strategy. Are you getting it? It's going to use the same loss function. Only the monitoring aspect alone I change. Can you see this is your training F1 score 97.92, but validation F1 score is 96. So at the end of every iterations, what it is going to do, it is going to put the confusion matrix. From the confusion matrix, it's calculating the recall, precision, and then finally computes the F1 score. Can you notice some mild, see sometimes your validation F1 score is 97.18, but in the next iteration it's going down. Another iteration is going up. Okay, slightly it is going up and going down. I will tell you how you can suppose you wanted to stop. See, there is a chance that your model may oscillate after reaching the best value. For example, this is a very complex terrain. It reaches the very good saturation point. Okay, once it reaches the saturation point, after some point, it will again start oscillating. That means it is in the path of ascending. Anytime your model can go into the ascending direction. So you have to very carefully, once it's getting saturated at certain level, okay, very finer movements are there. And at one point of time, I wanted to do the early stopping, okay, early stopping with the criteria. When compared to the previous F1 score, okay, if my current F1 score is better, okay, I always preserve the best F1 score. Say, for example, at this junction, I have got this is the best F1 score, 97.31. Now, can you see the values going down, 97.30? So whenever the value going down from the best, your model will not update the model parameter in the saving. I'm talking in terms of saving the model. Okay, when the value is going down, it won't save the model parameter. When it will save the model parameter, if this value is better than the previously saved score. So the previously saved score was 97.31, right? Now, at this iteration, the score is 97.36. So the current score is better than the previously saved score. Now your model will update the memory with this weight. So far the best score is 97.36, isn't it? Look at the next iteration, 97.28. The score has gone down. Then 97.35. Again, not good. 97.28. Again, smaller. So far the best is 97.36. So the early stopping criteria, okay, the model checkpoint will keep on checking. If the next subsequent iteration is going to be better than my earlier saved score, then I will update my memory. Otherwise, I don't update the memory. So that is the strategy we'll be using in the automatic saving process. So before I go with automatic saving process, so first we are going to do the manual save process. How to do the manual saving after training. Okay, now it is completely trained, right? Okay. See, this monitoring strategy is only for, okay, for our experimentation. See, during the experimentations, we wanted to see that whether our model overfits or underfits. Once you monitor it and you accordingly just go and fine tune it and introduce a dropout layer and you play with these number of neurons. And once you're satisfied with the architecture, right? Finally, once you're satisfied with the architecture, please make sure to, before you save the model, you bring it back to the default. Most of the beginners, they forget to do this. Please understand, by changing the metric, you are not going to disturb the learning pattern of the model. Your weight remains the same. You are just, metric is just for your monitoring purpose. You are monitoring the model based on precision, F1 score and stuff like that. But whatever the model has learned or whatever the cost function has reduced, that is remain unaltered. Please, this is again often, this question is popular question. When I interviewed candidate, many times I have asked this question to the candidate. There are few candidates got confused between the loss function and the metric. They confused with the loss function and metric. At least 3 to 4 candidates out of every 10 candidates, they messed up both the terms. So you should have clarity on that. Loss function is just to make the model to learn by reducing the cost function. That is the objective of the loss function. I can use any metric to, once the model has learned, model will come to me, hey, I have learned. You check me, you validate me using any metric and observe my performance in terms of confusion matrix, or in terms of F1 score, in terms of ROC, or in terms of precision or recall, whatever the way you can check. But I have learned like this. Okay, just because you are checking the recall, I cannot go back and change my learning pattern. Whatever my learning behavior was same. It's your choice to visualize me whatever the way you want to see me. That is the difference between the metric. So before you go for the manual saving or auto save using early checkpoint criteria, make sure to modify this again to the default. I modify this again to the default accuracy. Okay. Update the training process. Okay, just changing the metric accuracy, my learning pattern will not change, the same learning pattern, but this time it is going to show in the display the accuracy score, training accuracy and validation accuracy. Okay, once it completed the number of iterations, now I go here. Okay, I am directly save my model.save, specify the path. I name this as, because we are training the raw pixels, right? We are training the raw pixels. Okay, in future, if you learn CNN, you'll come to know that your CNN layer is going to learn meaningful patterns. Okay, meaningful pattern like edge informations. Well, for example, 5 will be learned like horizontal and vertical edge, and there is a curvature. 1 will be learned like it has 1 vertical edge. 7 is learned as 1 horizontal, 1 slanting, or even vertical edge, straight edge. So it is going to learn in more meaningful manner for the character. For some color images, natural images and all, as I told you, it will learn in terms of what is the average intensity of the leaf color, what is the texture of the leaf, if it is like a plant or a tree, what is the color of the branch, what is the edge of the trees. Okay, so your CNN layer is going to learn more meaningful pattern from the images, and those pattern will be fed as an input. Those feature will be fed as an input to the fully connected layer. Since we have not done CNN based architectures and all, with the fully connected layer, how best we are going to learn the model, that's what we are doing. That is why I named this model as MNIST raw pixel trained.h5. MNIST raw pixel trained.h5. Okay. As soon as you run this, okay, now I'm going to, already I've saved it, but I'll show you the file. If I second time when I run, it is going to overwrite my weights. It will be overwritten. Can you see the file here? This one, MNIST raw pixel trained. I have already having this file. Okay, maybe I delete this file. Okay, I'll move this to trash. Now I have, this is different file. MNIST raw pixel trained best. Maybe I'll delete this also. This also I move to trash. So I don't have anything starting with mnist, isn't it? I don't have any file starting with mnist raw pixels. So I have moved this to trash. When I flush this, I'll empty the trash. Go back to this. So inside my current working directory is DL. I just go as per alphabetical order. So in the M, I don't have any file starting with mnist, right? Now I go here. So before that, since I'm going to communicate with the Google Drive, I have to mount my drive. Then only it will write in this path. So it's successfully mounted. It's done. Now I'm going to save. So the saved model, if you wanted to load directly, I need this package, Keras package from TensorFlow, import Keras. So using this Keras method, Keras API, you can call the method keras.models.load_model. Now I have saved this. Let me go to my DL directory. Okay, the DL directory. Let me refresh this. I'm refreshing the DL folder. So the saved model, how to load keras.models.load model. I go to the same path and I'm going to read that file. mnist raw pixel trained. We can load it directly. So the loaded model, you can name it as mnist trained model. Okay. So before that, let me show the file over here. Can you see? Earlier we have deleted this and I also have flushed out the trash. Now we have got mnist raw pixel trained.hy file. Now we are going to load this file directly from the path. Let us assume that, okay, assume that you have closed Colab and you are opening the file in the evening. Okay, you are opening in a new runtime, or you are opening as a fresh. You just load the data alone. You don't need, you can skip all the training part and all compilation training. Directly you can come and load your model. Now I'm loading the model. So mnist raw pixel trained loaded. Okay, if you wanted to quickly cross check whether the right model is loaded or not, what I suggest you just check mnist underscore trained underscore model dot summary. To check the summary, you will get it. Okay, this is the architecture. So our model is successfully loaded with 46,580 parameters. Yesterday we have seen, in case if you have missed yesterday's session, see this calculation. This calculation is also very important to the context of interviews. Okay, mainly if they conduct a written round and all, they may ask these questions. So very commonly. So I have elaborately discussed this with the 2 to 3 examples. Go through this, how we calculate this. So successfully we saved the model and we have loaded the model, right? Using this loaded model, okay, I come to one of the production data. Yesterday I told you to download few images from the internet, random digits from the internet. Okay, one such image I am loading. Not necessarily you should also use the same file. You can use any image of your choice. Yesterday we checked it, right? We checked it without saving the trained model. After training, our model object is model, right? Using model.predict directly I used it. But now I'm going to use which object I'm going to use. I'm going to use the object MNIST trained model. This object I'm going to use. So MNIST trained model.predict I'm going to use. So for that, I should load and prepare my production data, right? So this is my production data and do the same preparation, color conversion, followed by resizing, followed by thresholding, followed by flattening, converting 2D to 1D. Now my production image is ready, right? Test image production. Now you directly go and run MNIST trained model.predict. MNIST trained model.predict. Here I'm using a different object. Yesterday we have used model.predict. We have got the score, right? This time we saved the model and then we loaded the model. Using the loaded model, directly I take that loaded model for the prediction. It's working fine. Same manner you can try with different digits, different pattern and try and see how your model works. Number 2 variation I'm going to show you. This time I'm going to make it auto save. So how to do this auto save option? For that you need two libraries, additional two libraries you need to import. Okay, these are the two libraries, model checkpoint and early stopping. So I have shared the updated code with you. I hope you today, whatever you have received is the updated code, including these topics. Please use this file, updated file. So it is like you have to write these two lines like a pair. First, you have to create a checkpoint and you should use that checkpoint inside your training process. When you do the model.fit, I have to pass the same parameters. Okay, I have to pass the same parameter. What are the parameters? Your X train, Y train, number of epochs, validation data. But usually we pass your metric, right? You pass the metric, that's all. But all these metrics and other things are written separately in checkpoint and early stopping. So I call something called callbacks. They should be written in the form of a list. So in the list, I have defined checkpoint and early. So how checkpoint and early, what are the things need to be assigned in the checkpoint and early? In the checkpoint, first of all, you have to specify the file name. Okay, the best model need to be saved in what name? Like earlier, I have saved MNIST raw pixel trained. That's all, right? Now I'm going to say MNIST raw pixel trained _ best.h. So every time it is going to see the validation accuracy when compared to the previous iteration. If the current iteration validation accuracy is better, that value will be saved. So how we communicate to that function? Save the best only, true. So it is auto save mode. Okay. Verbose one for the display purpose. Whatever is happening, you wanted to display. Okay, whether the saved is happening or not, you wanted to monitor that. So in the early stopping, you have to say which parameter you are monitoring based on validation accuracy. And I have given comments about the other parameters. For example, the min delta. That means minimum. See, you can give some threshold value. Only if say, for example, at least if the improvement happens when compared to the previous iterations, if the accuracy is improved by, say, for example, your values are given between 0 to 1, right? 0 to 1. For example, 0.9566. Afterwards, 0.95. 0.67 because the difference is only 0.001. You can give a cutoff only if the difference increases by 0.02. If it is 0.02 means 958, am I right? 958. So you can set a cutoff something like, okay, if the min delta is 0.02, then only you consider as an improvement. So don't consider this guy as an improvement. What you are indirectly saying that don't consider this guy as an improvement, consider this guy as an improvement because this improvement happens only 0.001. So anything below 0.02 should not be considered as an improvement. Anything above 0.02 should be considered as an improvement. That is what this delta is going to tell us. Okay. But I'm not passing any such delta. Okay. Even if 0.00001 some improvement is there, I wanted to record it. Okay. This is user's choice. If you wanted to give, you can give. Otherwise, I wanted to set it to default, which is even a very fractional improvement happen. I wanted to save it. This patient's 20 meaning is at one point of time, it will saturate, right? Say, for example, at the best score has reached 0.9745. This is the best score it has reached. Once the model reached the saturation zone, I wanted to see the continuous 20 iteration. If there is no further improvement, it will go to the early stopping. Suppose you have given 100 epochs, okay? But from 75th iteration to 95th iteration, totally we have got 20 epoch, right? The continuously 20 epoch, if the value remains same, there is no further improvement that happens, saturated, it will come out. It will don't wait for till the 100th epoch to go on. 95th, beyond the 95th iteration to come out. Even if this condition happens at the 50th epoch also, it will come out of after this. But make sure that saturation happens at satisfactory level. Okay, suppose if this condition happens at, say, for example, 6532, it's a very bad score, right? 65%. If the saturation happens at 65%, something serious, that means your model is underfitted. Maybe you have done something like a over dropout you have done, or insufficient number of neurons, or insufficient number of layers you have used. This is a serious problem of underfit. Okay, try to get some decent score above 90 or 95, good range what you expect. At that range, you try to set this patients. So immediately at the beginning shot itself, first step is you have to manually see the score. Okay, immediately the first shot before tuning the architecture, never go for this autosave mode. First, you have to run the iteration for 10 epoch, 20 epoch, and try to see the convergence. Whether the values are converging smoothly. Converging means whether your losses are gradually decreasing it. When compared to previous 0.0117, 0.0051 reduced, 0.0026 again reduced. This is what the convergence. Whether the convergence is happening smoothly or in terms of a score you see, it's increasing gradually. Okay, if any serious problem over there, accordingly you can change the optimizer or the architectural design you modify. If you're not getting a satisfactory score, your model is underfitting. Okay, even after 50 epoch, if your value got stuck somewhere at 60 means your design is having an insufficient number of layers. You have to introduce a layer and see the performance. Once after all the experimentation, then only you should come for this step. At the beginning itself, you should not come here. That is why in the session 4, I have not introduced this. Okay, only in the session 5, I'm introducing this. First, you have to manually verify. Once you got satisfactory result, then you come for this. Now I'm going to run this. I'll show you how this early checkpoint is going to save the scores. Always the best scores. Can you see whatever the first value, it is considered as the best score. Okay, what is the score? 98.229 something. So it is saved over here. Okay, now it is 96.53. is saved as the best score. So this is training accuracy. Okay, we have to monitor the validation accuracy. So validation accuracy. So here the best score is saved 96.53. Okay. Earlier the best score was 96.34. It's saved here 96.34. So 96.53 is better than 96.34. So your best is updated. Afterwards 96.53 same value, not updated. 96.05 smaller than the best, not updated. 96.69 better than the earlier best, right? So it's got updated. Likewise, it is working on. Again, see 96.87 is better than the earlier score. 96.87 got updated. Again, the values drop. This is not updated in the memory. We have to see if anything better than 96.87. 96.87. Anything better than 96.87. Yeah, 97.05. So far the best is 97.07. So it will take some time. Okay, finally we'll come back and see the best score. What is the best score? And now it will be saved. Okay, already every time it is being this is being saved over here and it's overwritten. Now this is the MNIST raw pixel trained best, right? This is being overwritten again and again. Whatever the best one. Once it is completed, in the same manner, okay, in the same manner, you can load the best model and you can use it for your production. Or even further validation with a bunch of records, you can try again, validate the model. Like the way we have validated the model with a bunch of training records. Validation records. Here you can update your classification report and you can monitor all the parameters, whether it's satisfactory or not. Okay, once the iteration is over, we come back here and we'll do like model.predict we have done. Okay, here we'll use what I'll be using here. MNIST trained model underscore best.predict with all bunch of validation record, right? So I wanted to see the best model is going to improvise. So far, yesterday we have not tuned anything. The overall average is 96 and the individual scores, the least was 95 and the highest was 98, right? So once this iteration is over, we'll load the best model and we'll update this matrix. Okay, so let it do in the background. I think around the 25 or 26 iteration is completed. Yeah, 38 iterations. So what is the best so far? 97 point something was the best. Okay, let it run in the background. By the time, I would like to define the problem statement for the next exercise. Next exercise, also it is a classification task. Okay, it's a classification task. I wanted to give an idea about a text data. What are all the perceptions and objective you can keep it for a text data.